Swayam Prabha. Digital India. Educated India.
Welcome back, students. So today we are going to do some practice problems on the mass transfer module. So let's begin with the first problem. What you can see on the slide, let's read the problem and try to understand. So the first problem says that there is a 20-liter stirred fermenter which contains the bacterium Bacillus thuringiensis culture at 30 degrees C, and it is being used for the production of microbial insecticide. So the volumetric mass transfer coefficient, which is given here as KLa, is determined using the dynamic method, which means, if you remember, the culture is present in the reactor and they are trying to find the volumetric mass transfer coefficient. Airflow is shut off for a few minutes and the dissolved oxygen level drops. Okay. The air supply is then reconnected. So if you remember, the profile for the dynamic method was that at certain time point the airflow is shut off, it falls down, and then before it reaches below the critical concentration of oxygen, the airflow is again resumed. So, and the concentration of oxygen in the bulk is measured with respect to time. So, they say that the steady state is established and the dissolved oxygen tension at this point is 78%. The following results are obtained. So, they have given their data in the form of table, where at 5 seconds the oxygen tension calculated is found to be 50%, and then at 15 seconds, so this was 5 seconds, it is found to be 66%. Now with this data, we need to find the value of the volumetric mass transfer coefficient. Okay. So if you remember the mass balance for oxygen, the rate of accumulation of oxygen in the medium, where Cl is the concentration of dissolved oxygen in the medium, was given by the difference between the OTR and the OUR. Now OTR, where it stands for oxygen transport rate, and OUR stands for oxygen uptake rate. Now oxygen uptake rate in turn could be defined as the club of the volume, the specific oxygen demand of the culture multiplied by the total biomass present at that time. And if you remember the assumptions in the dynamic method while calculating KLa, it was that we will assume that during this process of data collection and finding the value of KLa, the biomass is not changing. So we can assume the consumption term to be the same. And OTR is given as, we all know, volumetric mass transfer coefficient multiplied by the concentration gradient. So C star is your saturation concentration of oxygen concentration, and Cl is the bulk oxygen concentration at any time point. So how do we calculate the value of KLa here? Now with this equation for mass transfer of oxygen, the accumulation rate of oxygen in the bulk, we know that the steady state, at steady state 78% is the bulk oxygen concentration, which we can measure. Now at steady state, which means dCl by dt is 0, so OTR will be equal to OUR. So, because we do not know about the QO2 and X given in the problem, but we can find the entire OUR which is not changing by finding now the OTR at this time of steady state. So, what is OTR? The OTR will be KLa multiplied by C star minus 78. So, they are saying that the dissolved oxygen concentration at steady state is 78. So, we know that this is equal to our OUR, which we can give as QO2, specific oxygen demand of the culture, multiplied by the biomass concentration. Now, we know now that this is what is OUR. Now, at any time points, the dCl by dt can therefore be written as KLa multiplied by C star minus Cl, bulk oxygen concentration at that time, minus QO2x, which is OUR. Now, OUR can be substituted by KLa multiplied by C star minus 78, isn't it? Now, if we expand this, in turn the dCl by dt can be written as, so this term will get cancelled if you open up the brackets, and it will become KLa times 78 minus Cl. This will become this. Now, if we integrate this, if you need to calculate now KL given the data CL and T, then let us integrate this. So, integrating this will become ln 78 minus CL1. Now, let us assume this is CL1, CL2 limit, and this is T1 and T2 by 78 minus CL2 is equal to T2 minus T1, isn't it? So, this upon integration can be converted like this. Now, let us say this is T1, this is T2, this is CL1 and this is CL2. So, if we need to calculate the value of this, should be multiplied by KLa. Now, if we need to find the value of KLa and we know T2, T1, CL1, CL2, KLa can be obtained. So, this is what has been done. So, KLa will in turn become ln 78 minus 50 divided by 78 minus 66, 1 by 15 minus 5, T2 minus T1. So, this is what is given here. So, our KLa value can be obtained as 0.085 second inverse. Now, let us see the second part. An error is made, I will just erase this so that the question is visible properly. The error is made determining the steady state oxygen levels. Instead of 78, they have taken it as 70% by mistake. Now, we need to find what will be the in turn percentage error in the resulting KLa value. That should be doable. Now, we know that how KLa is to be determined given the value of CL1, CL2, T2 and T1. Now, the only change here which is being made is that in place of 78, the steady state concentration measured incorrectly is 70. So, here it becomes 70 minus 50 divided by 70 minus 66, which comes out to be 0.1609 second inverse. So, if the difference is calculated in terms of percentage, it comes out to be 89 point something. So, it has been shown as nearly 90%. Let us see the problem 2. Now, Serratia marcescens bacteria are used for production of threonine. Okay. The maximum specific oxygen uptake rate of the bacteria in batch culture is given to us. So, means this is nothing but our QO2, the specific oxygen demand of the culture. The bacteria are grown in a stirred fermenter to a cell density of 40 grams per liter. So, we know that the biomass concentration to be achieved is 40 grams per liter. Now, the volumetric mass transfer coefficient in this system is being reported as 15 seconds inverse. So, this is our volumetric mass transfer coefficient. At the operating temperature and pressure, the maximum solubility of oxygen in the liquid is 8 mg per liters. So, this is nothing but our correct, the saturation concentration of oxygen in the bulk. Now, we need to determine if the rate of cell metabolism is limited by mass transfer or not. Now, in order to find that, we need to first find or the rate of oxygen consumption due to the growth of the bacteria, whether it matches up with the rate of oxygen transferred inside the reactor. So, which means that only when OTR is equal to OUR, then it is meeting the demand of the culture. And if OTR becomes minimum, this is the minimum condition. If OTR becomes less than OUR, which means that it will start becoming mass transfer limited. So, ideally it should be greater than OUR, then it is not mass transfer limited, but the reaction limited. So, let us find out the OUR first. So, QO2 is given to us and the cell density is also given. So, OUR will be nothing but QO2 times X, which is the biomass. Now, we will make the units consistent. So, here specific oxygen demand has been converted to millimole per gram per hour. So, this can be converted to hour inverse. So, hour further has been converted into seconds. So, this becomes second inverse. So, millimole of oxygen has been converted to grams. So, into 10 by 3 is moles and 32 is for the oxygen, weight of oxygen per mole, and your hour has been converted to seconds by multiplying it with 3600. So, ultimately it comes out to be in terms of seconds inverse 4.44 into 10 to the power of minus 5. Now, cell density is grams per liter. So, maximum oxygen, so uptake rate would be in terms of, again they are converting it into kg per meter cube. So, this becomes 1.77 into 10 to the power of minus 3 kg per meter cube per second. Okay. Oxygen transfer rate. Now, we need to find, so this was OUR. Now, we need to find OTR. Maximum oxygen transfer rate can be what? So, in a reactor, the maximum rate at which oxygen can be transferred will be dependent on the KLa and the concentration gradient, which means the difference between the saturation, equilibrium concentration and the bulk concentration. So, maximum gradient can be when the bulk becomes 0. So, your maximum OTR possible is KLa times C star. Now, C star is given to us as 8 ppm and your KLa is 0.0 0.15 second inverse. So, this again gives us 1.2 into 10 to the power of minus 3 kg per meter cube per second. Now, if you compare the OTR with the OUR value, so this is our OUR and this is OTR. So, OUR is 1.77 and this is 1.2. So, OUR is much higher than the OTR, which means that this system is going to be mass transfer limited. To be specific, oxygen mass transfer limited system. Let us see the problem third now. A value of KLa is given as 30 hour inverse. So, volumetric mass transfer coefficient of the system is known for a fermenter at its maximum practical agitator rotational speed with air being sparged at 0.5 VVM. Okay. So, volumetric mass transfer coefficient under the operating conditions of maximum possible agitator speed and 0.5 VVM of air sparging rate is 30 hour inverse. Now, E. coli is grown in this fermenter. It has a specific oxygen demand of 10 millimole O2 per gram dry weight per hour. Okay. The critical dissolved oxygen concentration, which means that oxygen concentration level below which the fermentation cannot be run. So, the critical dissolved oxygen concentration is the minimum oxygen concentration bulk possible is 0.2 mg per liter. Okay. The solubility of oxygen from air in the fermentation broth is 7.3 mg per liter. So, this is nothing but our saturation oxygen concentration value at the given temperature and pressure. We need to find out what is the maximum concentration of E. coli which can be obtained in this fermenter. So, maximum biomass possible. So, we know the specific oxygen demand and let us assume X is that maximum biomass possible. So, this is our OUR, oxygen uptake rate. So, this will become now the maximum oxygen uptake rate. Now, under any circumstances, because the KLa is fixed, the sparging rate is fixed. So, the maximum possible OTR we can find out, which will be KLa times C star, where Cl will become 0, then only this will become the maximum possible OTR given the KLa value and the C star value. C star is 7.3, KLa is given to us as 30 hour inverse. So, now the maximum possible biomass which can be supported by this fermenter can be calculated by equating OUR and OTR and finding the value of biomass. So, let us equate QO2 times X is equal to KLa C star. So, your X maximum possible which can be supported can be calculated when you know KLa, C star and the specific oxygen demand. So, this is what has been done possibly here. See, at steady state. So, you are making the units consistent. The biomass possible is found to be 0.67 grams per liter. Let us see the second part. What concentration could be maintained if pure oxygen was used to sparge the system? Okay. So, we need to find that if pure oxygen is being sparged inside the system under the given operating conditions, then how much amount of biomass can be supported in that case. So, still the maximum amount of biomass which can be supported still remains the same, KLa times C star by QO2, but here what has changed is the C star value. So, we need to first find the C star value. So, now we know by Henry's law, we will use that equality. So, for 1 atm atmospheres where the mole fraction is now completely oxygen, otherwise it is 0.21 is equal to, so this is 7.3 mg per liter. What will be the X value? So, this is your saturation. So, your saturation concentration of pure oxygen can be calculated based on Henry's law as 34.8 mg per liter. So, once the saturation concentration of oxygen in the bulk, then the X by the same equality can be calculated as 3.24 grams per liter. So, as we increase the mole fraction of oxygen in the incoming air, the biomass which can be supported by the same fermenter system under the given operating conditions increases.